Now let's talk about plyometrics. And we talked about plyometrics and we said that they can be effective in helping us increase our power output. Or another way of thinking about it is increase the explosive ability of that individual or that athlete. And in certain sports, this is going to be essential for success. For example, combat sport, MMA, if you're not explosive with how you're striking them, you're not going to be able to land those punches and or create a lot of damage when you make that. So plyometrics can help us increase our power output. But how does it do that? What's the physiological explanation for how it happens? Well, we have two models. And if we remember when we talked about models, we said they were oversimplifications, but they help us understand what exactly is going on. So we have model A and we have model B. Model A is what we call our mechanical model. And it has two components built within it. We have the musculotendinous components and how they interrelate to increase power output, as well as this length-tension relationship and how that explains why we can produce more force from that. So both of these are mechanical. Model B is dealing with the neurophysiological. Essentially, the key word here is neuro. It's talking about your brain and how this type of training affects how your brain is able to recruit those motor units or those muscles to increase your power output. So it makes your brain a little bit more efficient in terms of how it's working. And it also has two components. So it has potentiation and our stretch reflex. And I said the stretch reflex is really going to be important. We're seeing it again here. Now, a key way of thinking about this or helping you understand the difference between the mechanical and the neurophysiological model is thinking about a computer. So if you take a computer, you can increase the hardware of that computer. So let's say my computer has a couple gigabytes worth of RAM and it has a certain amount of memory and it has a certain processor chip inside of it. Okay, that's the physical hardware it has. And I could go into the computer and I could take things out and or add different components to make it faster and more efficient, right? So I could change the hardware aspect of it or the mechanics of how my computer works. And the other thing I could do to change the performance of my computer is I could change the software it's running. And with your iPhones or whatever you have, right, you get software updates all the time. And the idea of software update is to help that device run more efficiently. They're not changing what your phone has in terms of its hardware, but it's trying to maximize what it's able to get out of that hardware, right? That would be the software or the neurophysiological. So if I took this computer and it's running Windows 10 right now, and I gave it Windows Vista or Windows XP, it would not perform as well. It would not be able to do all the things I want it to do because while the hardware stays the same, the software dictates what I'm able to do with that hardware, and vice versa. If I have Windows 10 right now and I add all this different hardware, but I'm not more efficient at using it, then I've essentially wasted it. So that's kind of the idea of hardware versus software and understanding how it relates to performance. We can change the hardware or like our muscles and tendons and how they function, or we can change our nervous system and how effective we are at using those structures. So let's talk about the first component of our mechanical model, and that was the musculotendinous components and how they relate to increasing this force production. So in a muscle, we have three main components that we care about. We have our series elastic components, or our SEC. Those are going to be our tendons. We have our contractile components. This is going to be our actin, myosin, and those cross bridges. And then we have our parallel elastic components. And this is going to be our epimyosin, endomyosin, sarcolemma. Think of this as the cell wall, or the part that holds that the muscle cell together. So we have these three different types of components, and all three of them are going to contribute to creating force and helping us be more explosive. So let's talk about the series elastic components first. Well, if you remember, a tendon connects that muscle to that bone. And so when that muscle is stretched, it's going to be pulling our tendon. And it's very similar to this giant band. As the muscle contracts, it's going to be pulling that band further apart. Well, what happens if I let go of this band? It's going to snap because it's storing elastic energy. So your tendons have a certain amount of elastic energy and elastic properties. So as you stretch them, when you let go of that, there's going to be that snapping, or it's going to forcefully return back to its original shape. And we call that elastic energy. We call that potential energy. right? And if you've taken physics before, you've talked about potential energy. And so as you're stretching that tendon, it's in series because the muscle is going to be pulling the same exact direction as the tendon is being pulled, right? That's why it's called a series elastic component, because it's in the direct same line as the muscle itself. Now, your actin and myosin, we said previously, it kind of looks like our fingers, right? And if we have actin components that represent my right hand, and then we have our myosin on this hand, they're going to connect, they're going to pull on one another, and they're going to bring each other closer until they fully overlap. And then, when they relax, they're going to be returning to this shape right here. They're going to stop overlapping as much, and that's what a contraction looks like. Another way of visualizing this is, let's pretend that I am the myosin, and this is my actin filament. So when you get a muscular contraction, you're going to grab on to the actin, and the myosin's going to pull it. Then it's going to grab on, and it's going to pull it. It's going to grab on, it's going to pull it. It's going to grab on, to pull it. And it's going to keep doing this until it runs out of actin to grab on and pull to, or till it reaches its limit. So our contractile components, the actin and myosin, they're going to produce most of the force that allows us for a muscular contraction, or it helps with that explosive ability. So they're just going to be pulling on one another like this and overlapping until they can't any further. That's going to be the contractile components. Well, what about our parallel elastic components? Well, if we think about our cell wall, it surrounds our muscle. It surrounds our actin and myosin. It surrounds our myofibrils. So if you want to think of it kind of like this band here, right, it's also going to be elastic. And so it can stretch some. So as the cell expands, right, as it starts getting stretched, what does the cell wall want to do? It wants to return back to its normal shape. So it's getting stretched out this way, it's getting stretched in 360 degrees. When that muscle relaxes or when you release that stretch, it's going to produce some energy and it's going to help. Now, it's called a parallel elastic component because it's not going to be pulling the same direction, or it's not in line with that muscle. It's going to be surrounding the muscle itself, kind of like I have here. So the muscle is here, as it's stretching out, it's going to be in line. So as it gets pulled, in the same way the muscle gets pulled, it's going to bounce back, or the contractile components get pulled, it's going to bounce back and help facilitate a little bit. So in terms of magnitude, we would say that the contractile components are going to produce most of the force. Our tendons are going to then be the second place one because they're going to be directly in line. And then the parallel elastic components, they're going to help a little bit to facilitate that stretching. So if we're doing a plyometric and we stretch first, we're stretching, we're storing that potential energy in our tendons and in that parallel elastic components. And then when we jump, these two muscle groups are going to be contracting together. You're going to get that overlap, and that's how we're able to jump higher. So by stretching first and jumping, we have that potential energy, and that's why it works better. Now we're going to talk about the length-tension relationship. And for this, I'm going to give you an example. So we're going to do 3 different jumps. The first jump I'm going to do, I'm going to limit how much I'm allowed to bend. So I'm just standing straight up. I'm going to jump as high as possible without bending. Okay, on the second one now, I'm going to get as low as I can, and now I'm going to jump. And on the third one, I'm just going to try to jump as high as possible. Now, what you might have noticed is that that third jump, where I allowed myself to bend some but not as much as possible, actually caused the highest jump height. And the reason for that is our length-tension relationship. And it's going to have to do with our actin and myosin. So if we think about our actin and myosin, we said that they start to overlap, and that's what's helping us with those contractions. And what we're doing when we have very little overlap is we have very few cross bridges, and we have very few connections between our actin and myosin. And the way I like to explain this or think about it is think about a tug of war. Okay, if you want to win a tug of war, it's helpful to have as many people as possible pulling on that rope. And so if each of these chairs represented a person, if I wanted to win a tug of war, I would want my rope to stretch across 3 people so that all 3 people could grab on and be pulling on that rope, right? That would be advantageous. Well, in a fully stretched position, so if I went all the way down before I jumped, what we're doing is we actually decrease the number of cross bridges, or the number of actin or myosin actin cross bridges, or where they're connected. So what that would look like, that jump where I was all the way down fully stretched, what would be happening muscularly is we would only have one of these 3 chairs actually pulling on that actin, right? So we would only get the force from 1 connection point. And that's why we're not able to jump as high in that position. Why was the jump where I was already fully extended decrease in terms of its performance? Well, if we think about our actin and myosin, they look like this. And so in a fully flexed position, they're going to be almost totally overlapped. And so while we'll have more cross bridges, we'll have the rope across all 3 people, there's not as much room for movement, right? Because it's already almost fully maxed out. And so the only movement we'll get is about that much, right? So we're almost fully maxed out, and then we get that little movement. And so that little movement isn't enough to create enough force and or speed or power for our muscular contraction. So we have 3 people pulling on it, but they can only pull a little bit before we run out of rope. So what would this look like in terms of our rope? We have all 3 of our chairs able to pull on it, but once they start pulling, we actually run out of rope very quickly, and so we can't create as much force or as much power. And so that's the downside of being in that totally overlapped position. We have a good number of people pulling on the rope. We have a lot of those cross bridges, but the cross bridges don't have enough time and or space to generate maximal amounts of force. Okay, so what's the Goldilocks principle? What I did, or what I showed an example of, is having a decent amount of starting overlap. So we're not just having one of these chairs pulling, but we're also not maximally or almost maxed out in terms of our length. So it's somewhere in between. So we're about here. So we have about 2 or 3 of these overlaps, but as they start pulling, as they start contracting, there's still plenty of rope before we run out. And so that's why a muscle that's in the correct length or correct starting position will actually be able to generate more force and more power than one that is either fully extended or fully flexed. Let's talk about our second model now, our neurophysiological model. And the first part of this is potentiation. And we talked about this when we were talking about our ramp protocol. And we said potentiation means it is easier to recruit a motor unit or activate a muscle when it's been previously activated ahead of time. So if I contract my biceps now and I relax and I contract it again, it's easier for my brain to recruit and send those signals to my biceps because it was previously activated. And so that's this idea of potentiation. So in a plyometric, when you're squatting down or you're absorbing that force, you're getting an eccentric contraction in those extensor muscles, right? So as you're absorbing those force, you're getting an eccentric contraction. Well, a fraction of a second later, when you're jumping back up, now you're recruiting that same muscle group, you're able to do it more effectively because of potentiation. The last component is our stretch reflex. And remember, a rapid stretch causes this reflex to kick in. So when you're landing after a jump, you're getting a very rapid stretching of those muscles in your legs. And so your stretch reflex, it's sending a signal that this muscle group is being stretched and is being stretched very rapidly. And so a signal is going to leave that muscle spindle, go to your spinal cord, and it's going to tell your brain, hey, this muscle is being stretched very quickly. And so your brain's response is going to be, hey, let's get a hard contraction so that we don't have any of that damage or that limitation. And so as it's being stretched, you send that signal to those muscles. Your muscles then contract harder because of that neurological signal, and you're able to jump higher and faster. And so that's your stretch reflex. Now, if we're thinking about plyometrics, it's not an either-or proposition. So it's not either the mechanical model is working or the neurophysiological model. They work together and they actually will coincide at the same time. And so they both are pieces of the puzzle that explain why we're able to jump higher and faster.